Welcome to Mathematics with Tom. I am Tom, and today we are going to solve the system of differential equations that has unique real eigenvalues. So I've written this out. This y, sometimes I've written it capital Y or y prime. That's the vector y. A is the matrix, which I've recorded here to the right, and y is another vector. And just for clarity, let's do this. Notice that the vector y is really the vector of functions of y. So y1 of t and y2 of t. And so the vector y prime is y1 prime of t and y2 prime of t. Well, this is really what we're solving when we say this, is we're really solving the system of differential equations. Y prime equals a y. These are vectors plus q. Well, what is q? Q is the source function, but in this problem, q is 0. So really, we're finding the null solution. So let's do that. Let's find the null solution. And remember, it begins with, we've shown how to find eigenvalues and eigenvectors, and that's what we're going to do. And that begins by taking a look at a minus lambda I, and in this case, that's going to be a minus 2 minus lambda 1, minus 2 minus lambda. Okay, now we're going to do this a little bit faster, because what we learned then is if we take the determinant of a minus lambda I and we set that to 0, well, we said that this is really, it's also lambda squared minus the trace. Well, in this case, the trace is going to be minus 4 times lambda plus the determinant. Well, that's going to be 4 minus 1. That's going to be 3. And so really what we're looking at is we're solving this problem of lambda squared plus 4 lambda plus, so it's a plus 3 equals 0. Well, that's going to factor into lambda plus 3 lambda plus 1 equals 0. And so there we have it, our eigenvalues. So lambda 1 is minus 1, and lambda 2 is minus 3. Okay? So we use our eigenvalues now to find our eigenvectors. So for lambda 1 equal negative 1, well, then let's take a look. Well, what is a? I'm going to substitute in a minus 1 into the lambda I, so that's really just plus 1i times, we'll call it v1 for the eigenvector 1 that's associated with the eigenvalue, lambda 1. And remember, we're solving when that's 0. Well, this becomes a minus 2 minus negative 1, so that's really plus 1. So that's going to be a minus 1, and then we're going to have a 1, and then another minus 1, times the eigenvector, v1, and that has to give me 0. Well, notice right off the bat we know our work is correct, because the first column, if you multiply it by negative 1, you'll get the second column. So those are dependent. If that's not, that quick check should always work. If that's not the case, then there's something went wrong. And if you look at this, notice it just says if we added those two things, it looks like if we add the first one to the second one, we should get the 0 vector. So it looks like that if v1 is just, we add one of the first ones and one of the second ones, there is our first eigenvector. Okay, now let's repeat this. So when lambda 2 is negative 3, well, then we're going to have a plus 3i times our second eigenvector. That's going to be 1, negative 2 plus 3. Another one, oh, and look at that. That is going to work as well, times our second eigenvector has to be 0. Well, notice that if we take the first column, we subtract the second column, that'll give us 0. Or if we subtract the first column and then add the second column, that would give me 0. So in other words, it looks like my second eigenvector is simply minus 1, 1. And there we are. We're almost done. Now we just put it together. So that lambda 1 and v1, that's our y1. So my solution of y1 is, oh, I'm sorry, not like that. My solution is the vector y1. So the vector solution, we'll write it this way, our complete solution, or null solution in this case, is c1 times the eigenvector. Well, the first eigenvector we said was 1, 1. And times e to the minus t. Plus, then our second solution is c2 times minus 1, 1 e to the minus 3t. And there we have it. Now, whenever you're working on one of these problems, if something's not right, you should always check. So let's just check. So let's check. Okay, so let's find y prime. Well, y prime just says we take the derivative of c1 e to the minus t. So that's just going to give me a minus c1 times the vector 1, 1. And I got that minus because from the derivative of e to the negative t. Plus, now we're going to take, this is going to become a minus 3 c2 times the eigenvector minus 1, 1 times e to the minus 3t. All right, now let's check. Let's see what we get when we take a times y. Well, remember that a is this matrix of minus 2, 1, 1, minus 2. And we're going to apply that to this first eigenvector, which is 1, 1 times c1e to the minus t. And we're going to apply that, the matrix A, minus 2, 1, 1, minus 2. We're going to apply that to our second eigenvector, minus 1, 1 times c2e to the minus 3t. Now, you can sit here and calculate this through, but if your eigenvector is correct, then remember that the matrix times the eigenvector should give you the eigenvalue times the eigenvector. In other words, this really should just give me a negative 1 times the vector of 1, 1. c1 e to the minus t. And you can just, let's just double check. That's going to be a minus 2 times 1 plus 1 times 1. That's going to be a minus 1. So if you factor it out, there's the first piece. And then if we go 1 minus 2 is also going to be a minus 1. Factor that out. There it is. Okay. Plus, well, what else do we have here? The eigenvalue is going to be a minus 3. The eigenvector is minus 1, 1. c2e to the minus 3t. And there it is. And it works like we had expected. So the y prime is equal to ay. I hope that helps, and thanks for watching.